Hello everyone, this lecture is exclusively recorded for second year BSc student of BK Birla College, Kalyan. This is mathematics class, calculus. In this lecture, we will study the maxima, minima and saddle point and Hessian matrix. So let me write down the topic which we are going to study in this maxima, minima and saddle points. We will also study Hessian matrix and problems related to maxima minima. So let's start the lecture. So let me define the maxima and minima. So definition, let U is subset of Rn be a non-empty open subset in Rn. Let f is function from U to R be a scalar valued function. Let P belongs to S and f is differentiable at P. Sorry. If gradient of f of P is equal to 0, then the point P is called as stationary point of f. Of f. So this completes the definition of stationary point. So first definition. Second definition of absolute maxima. So f from S to R. So instead of S, we will say U, where U is open set in Rn. So is said to have an absolute maxima at point P belongs to S if and only if f of x is always less than equal to. So here x is basically instead of f of x, I should say f of x1 comma x2 comma dot xn is always less than equal to f of p1 comma p2 comma pn. So here p is basically p1 p2 dot pn. Right. So that is, we will call it as f of x always less than equal to f of p. What is x in this case? X is basically x1, x2, dot 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 xn for all x belongs to S. So if f of x is always less than or equal to f of p for every x belongs to uh, u, then f of p is called as absolute maximum value of f. Right. So then f of p is called as absolute maximum value of f. Then third definition, relative maximum so for relative maximum your f of x should be always less than or equal to f of p for all x belongs to, you have to draw a ball around p with radius r which is fully contained in u. So now what is x in this case? X is basically x1, x2, dot 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 xn, and p is basically p1, p2, dot 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 pn, and r is basically a real number. So if you draw a ball around p with radius r, then the f of x should must less than or equal to f of p for every x belongs to b, that ball around p with radius r. Then f of p is called as a relative maxima. Then f of p is called as relative maxima. Then this was definition 3rd. Definition 4, absolute minima. So I'm not writing that let f be a function from u subset of Rn to R, p f is differentiable at point p. So that prerequisites in the initial part of definition is assumed. For absolute minima, you should say that your f of x must be greater than or equal to f at p for all x belongs to u subset of Rn. Now what is x in this case? You should know that x is x1, x2, xn, and p is p1, p2, pn. Then f of p is called as absolute minima of f, absolute minimum value of f. Then number 5th, relative minimum. So now here it is f of x is greater than or equal to f of p for all x belongs to ball around p with radius r which is contained in your S. Then saddle point 6. Well, saddle point we will define little later. So before that, let me define the critical point. So number 6, critical point. So let f is from u subset of Rn to R be a scalar field a point P belongs to U is said to be critical point if either gradient of f at P is equal to 0 or dou f upon dou xi at P does not exist. For some I 1 to n. So either gradient should be 0 or the delta, that partial derivative, does not exist. Well, you could see that every stationary point is by default a critical point, because when the gradient is 0, then that point is called as a stationary point. So every stationary point is critical point. Now let me define the Hessian matrix now. So Hessian matrix. So let f is function from Rn to R be a scalar valued function, scalar field with continuous second order partial derivatives then Hessian matrix is denoted by h of f and defined as h of f is equal to, so dou 2f upon dou x1 square, dou 2f upon dou x1 dou x2, dou 2f upon dou x1 dou x3 dot dou 2f upon dou x1 dou xn. Now dou 2f upon dou x2 dou x1 dou 2f upon dou x square x2 square dou 2f upon dou x3, so x2 dou x3, so on and so forth. So dou 2f upon dou x2 dou xn, that is second row. So in last row, so dou 2f upon dou xn dou x1 dou 2f upon dou xn dou x2 dou 2f upon dou xn dou x3 dot dou 2f upon dou xn whole square. So it is a square matrix. Note that here this is always a symmetric matrix. This and these are always equal because the second order partial derivatives are continuous. So one should note that dou 2f upon dou xi dou xj is always equal to dou 2f upon dou xj dou xi for all I comma j. If you take any I comma j, then the mixed partial order derivatives are always equal. So because of this, the matrix is always symmetric matrix. So when we say matrix is symmetric, if the transpose is same as, so H transpose, even if you evaluate, then you will get the same matrix. So let's have a quick example. If f of x, y, z is equal to x cube plus 2xyz, then find hf at 1, 0, 1. Well, how will I define hf? Hf is dou 2f upon dou x1 square. So xyz, so x square dou 2f upon dou x dou y dou 2f upon dou x dou z dou 2f upon dou y dou x dou 2f upon dou y square dou 2f upon dou y dou z dou 2f upon dou z square dou 2f upon dou z dou y. It should be dou z dou x dou 2f upon dou z square. So we can easily calculate this derivative. Partial derivative with respect to x is 3x square, and then again with x you will get 3x square, 6x. So second time, that first time it is yz, but then when you evaluate with respect to x it will get 0. Then for the second time dou 2f upon yeah, well, it is better to calculate this first. So what I'll do, I will go on the next page. So f of xyz is x cube plus 2xyz 2xyz. So dou f upon dou x is 3x square plus 2yz, and dou 2f upon dou x square will be 6x. Dou 2f upon dou x dou y is 2z, which is same as dou 2f upon dou x dou y. Then dou f by dou y is 2 times xz, and dou 2f upon dou y square is 0. Then from this we can even calculate dou 2f upon dou z dou y is 2x. Dou f by dou z is basically 2xy, and dou 2f upon dou z is 0. Okay, so let's substitute the values now. The Hessian matrix of f. So let me write down this 6x diagonal entry 0 and 0. 6x 0 0. 6x 0 0. Then xy or yx, that is 2z. Xy is 2z. It is 2z. Then xz xz xz. Okay, so this if I differentiate this with respect to x now, so dou 2f upon dou x dou z, I'll get 2y. So I need to write down this 2y. Now this is yz. Have I done this? Yeah. Dou 2f upon, this is 2x. This is evaluated at 1 0 1. So if I evaluate this, x is 6, z is 2, y is 0 2 0 2, 0 to 0. So this is how the Hessian matrix looks. Okay. So this Hessian matrix will help us a lot to find out the maxima, minima. So there is a test, second derivative test, through which the Hessian matrix will play a very crucial role. So let me state one of the theorem. So we will not prove, but at least I will state. So let f is from U subset of R into R be a scalar field where U is non-empty open set in Rn. Let f is differentiable at p belongs to U. Then f has local maxima or local minima so this so if f has a local maxima or local minima, then your gradient of f at p must be 0. So this proof we will discuss little later, but then we will assume that if the f has a local maxima or minima, then the gradient must be 0. Now let me have the second derivative test. Second derivative test for maxima minimum. Before that, let me define a determinant of Hessian matrix. So if f is from R2 to R, if it is given, then Hessian matrix of f will be of this form: dou 2 f upon dou x square, dou 2 f upon dou x dou y, dou 2 f upon dou y dou x, and dou 2 f upon dou y square. So what I'll call this as, I will call this as A, this as B, this is B because they are same, and this as C. So the delta, we will call it as a determinant of Hessian matrix, is AC minus B square. So this is how the delta will look like. So now we will be defining the second derivative test for the maxima or minima. The test is as follows. So let S be non-empty set, S is subset of Rn. So instead of S, I use the symbol U. Let's use the symbol U throughout the U. And f is a function from U to Rn, R. Be a scalar field. So instead of Rn, I will be particular, so it is R2. So be a scalar field. So f is a basically function from R2 to R, right? So then number one, if that delta greater than 0, and now here a means this double derivative of f, and a greater than 0, then f of f then f has relative minima, uh, instead of relative I'll say as local minima at also I should say that gradient of f at a comma b is equal to 0. Then f has local minima at a comma b. Second case, if a less than 0, delta greater than 0, then f has local maxima at a comma b. And third case, if delta less than 0, then f has saddle point at a comma b. And there is one more condition, fourth one, so let me write down fourth here. If delta equal to 0, then test fails, you cannot apply the test. Okay, so let's have one example. So we will use this theorem to find out the maxima, local maxima and local minima. So the question is, find extremum values of f. So when I say extremum, that means it is either maxima or minima. So the function is given as f of x comma y is x square plus xy plus y square plus 3x minus 3y plus 4. Our first step is we have to find out the stationary point. So gradient of f I need to find out. So gradient of f of x comma y, we should equate it to 0 comma 0. So that means dou f upon dou x comma dou f upon dou y should be equated to 0 to get this stationary point. So what is dou f by upon dou x? So dou f upon dou x should equal to 0 and dou f upon dou y should equal to 0. If you substitute this, because these two things are equal if corresponding vectors are equal, so this is equal to 0 and the second vector is matched to this second component. So what is dou f by dou x? So 2x plus y plus 3 equal to 0, and dou f upon dou y is y plus, it is x plus 2y minus 3 is equal to 0. Right, so if I solve this simultaneously, this is number 1 equation, this is number 2 equation. So you solve this simultaneously. So these are two simultaneous equation. You need to multiply some equation. इसको 2 से multiply कर देते हैं. So 2x plus 4y minus 6 is equal to 0. Then इसको 3 बोलते हैं. So 1 minus 3 will give me the some y value. So 1 minus 3 y minus 4y minus 3y, 3 plus 6 so plus 9 is equal to 0. This would imply y is 3. So if you substitute y is equal to 3, any one equation, substitute y equal to 3 over here. So what I'll get, 3 plus 3 is 6 that side, so minus 3 will come. x is equal to minus 3. So x comma y, which is equal to 3 comma minus 3, is stationary point. Now second case is you find out the Hessian matrix of f, which is dou 2f upon dou x square, dou 2f upon dou y square, dou x, dou y, dou 2f upon dou y, dou x, dou 2f upon dou y square. So what is it? Dou 2f upon dou x square. So already we have calculated. So it will be, if I differentiate this one more, then it will be 2. I will have 2. And if I differentiate this with respect to y, then again I will have 2. And the double derivative again, that will goes to 0 only. So my a is 2, b is 0, c is 2. So delta, which is ac minus b square, which is equal to 4. Right. So you could see that delta is greater than 0. Delta is greater than 0. Also a is also greater than 0. So this would imply 3 comma minus 3 is local maxima point for f of x comma y. Right? Am I correct? 3 comma minus 3 only. I think I have had x is instead of 3 comma, I think it is minus 3 comma 3, not 3 comma minus, because x is minus 3, y is plus 3. So here I should say minus 3 comma plus 3 is. And what is f minimum value? The f minimum value, you have to replace it by f is x square. X square means it is minus 3 square plus xy, so minus 3 plus y square, that is 3 square, plus 3 times x, so minus 3, minus 3 times y, it is 3, plus 4, so it is 9 minus 9 plus 9 minus 9 minus 9 plus 4. So this minus 9 plus 9 minus 9, so it is minus 5. So f minimum value is minus 5. So we may have many examples. So in upcoming lectures, or maybe I will put some more problems for the practice to find out the extremum value. So that's it for the lecture. Thank you.